Hello friends, hope you all are good. So today we'll start the chapter limits and go into the depth of the chapter that what the chapter limits says to us. So let us start the chapter limits. So first uh, we we will come to the introduction part. So what does the chapter limit say? Mm, Let us introduce the notion of limit of a function, which plays an important role in mathematical analysis and the study of calculus. The concept of limit of a function is one of the fundamental ideas that distinguishes calculus from the algebra. We, we will use limits to describe the way a function f varies. Some function varies continuously, that is, small changes in x produces small changes in fx. For example, let the function be y equal to x square. The function is like this. Uh, uh, For a small change in x, there is a small change in y. Okay, so let us continue. And, and other functions which have values that jumps or vary erratically. Mm, for example, uh, uh, let's say the function is y equal to mod x. Sorry, y equal to gent x. Okay, and the function here is y equal to mod x. Okay, the function of y, the graph of the function y equal to mod x is y equal to x uh, for, for all x greater than 0 and y equal to minus x for all x less than 0. And what is the graph of y equal to gent x? Here this here this is the gent function, that is also called as greatest integer function, uh, and it represents the greatest integer less than or equal to x. For example, gent of 1 by 2 is equal to 1. If we draw a number 9, let's say 0 1 2 3 minus 1 minus 2 and minus 3, and gent represents the just previous number or that number. For example, if the number lies in the here in between 1 and 2, mm, for example 1.2, if the greatest integer function of 1.2 would be just previous number, that is 1. Okay, and similarly for minus zero point 0.9 it would be minus 1, minus 1 point for minus 1.2 it would be minus 2. uh, and if for x belonging to integer, for example x equal to 2, uh, and gent of 2 is equal to 2, uh, and gent of any natural number, any integer and belongs to integers, either it may be natural number, whole number, negative integer, positive integer, it it is the same function. Okay, then we plot the graph for y equal to gent x. It would be from 0 to 1, it would be a straight line here, and from 1 there would be a jump, uh, and there would be a discontinuity at 1, and the graph would shift that for example 1 for 1.1 the gent would be 1, for for 1.9 the gent would be 1, and so on. It goes like this. It is a staircase like graph. And it goes so on, and here also. Okay, so uh, uh, so sometimes we face problems whose solutions involve the use of limits. According to, for example, according to a formula of geometry that we have already know, that the area of the circle, mm, that this is a circle with radius equals r. Mm, its area is equal to 4 pi r square, that we already know. And how is such formula derived? Like we know that its area is pi r square, but how do we find? For example, the area of a rectangle is length into breadth. Area is equal to length into breadth. But how? Yes, this might look like an unusual question that we haven't asked, but it is actually the most interesting to question that we should have asked. Okay, so in this chapter we will also know how to find this. The usual way is to inscribe regular polygons in for finding the area of circle, uh, and find the areas of the polygons and determine the limiting value. Mm, we- that is, if we uh, uh, like if we make first triangle, we, okay, a regular triangle, uh, then we make it a regular square, then pentagon, then so on. So on, uh, we will be forming a regular polygon uh, with so much sides. And you will observe that as we are increasing the number of sides from 3 to any natural number, uh, this area, that is excluded area, is decreasing. Uh, number of sides is equal to 3 and number of sides equal to n, and as n tends to infinity, l- like n tends to very large number, this area, this portion, area of this portion tends to 0. Mm, that means that the area excluded uh, uh, tends to 0. That means that the area of this regular polygon, which which would be formed if we find its limit as n tends to infinity, that would be the area of circle, that we know that is pi r square. We will also know this in further, after this part. Okay, me if rather in the last part of this chapter. Okay, so moving forward, mm, now we will define neighborhood of a point. Uh, like for example, we take a graph of f of x equal to 4x. If we draw its graph, it would look like this. For x equal to 1, uh, uh, its value is 4, and for x equal to 2, its value is 8, and so on. Like like if we take this function, we, we will find that f of 1 is equal to 4. But uh, but uh, but here we will be focusing on the neighborhood of this function. Like what is the value at 1.00001, or value of function at a 0.99999, so on. Like we are looking in the neighborhood of this function. If we take a general example, like f of x, any general function, having any general graph, and this is the value of a, this is the x coordinate and this is the y coordinate, and if the value of x is equal to a, then the value of fx is f of a. So we are interested in the neighborhood of of this as x tends to a. Okay, so so we We will draw the number line, like this is a, and so on, a plus something, like a plus 0.001 and a minus something, like a minus 0.001. Let's take an arbitrary number del, a plus del and a minus del. Okay, and if the function is defined between if it means that if the function is continuous between these two values, and and we will be focusing on this in the neighborhood. And also we will arbitrarily take that del approaches to 0. So you might have understood that we are interested in the values in the neighborhood of f of x, in the neighborhood of the values x equal to a. Uh, and also further you will see that for finding the limits we will only use the limiting value of x tends to a, but not the value of function at x tends to a. Mm. That means it is not necessary that limiting value of a function is the value of a function. Okay, so let's move on to the next page. Like for example, if we take a function like this, this represents open circle and this represents the close circle. Okay, it says that when we are approaching to x equal to a, mm, then in the neighborhood of x equal to a, mm, the value of function is y1, and exactly at x equal to a, the value of function is y2. So these may be necessary, these may not be necessary in general, but in the continuous graphs they will be equal. Rather you will study in the chapter continuity that this is the condition for a function to be continuous. Okay, so let's move on and find what is the limit of a function. And let's consider a function y equal to fx of a continuous variable x. Suppose that the independent variable x approaches a number a. This means that x is made to assume values which come arbitrarily close to a, but are not equal to a. To describe such a situation, we say that x tends to a or approaches to a if there is a number L such that as as x as x approaches to a, uh, like that means as x approaches to a, the the value of function f of a will also approach to a certain value L. Then this value L is called the limit of is called limit of fx as x tends to a, and this is represented by limit limit of fx as x tends to a equal to L, or we often represent it as limit of fx as x tends to a. Okay, And also it is saying that as we are approaching x from the left, either from left hand side or from the right hand side, that this is x. If we are coming from this side or from this side, like if we are, like if like it is a minus point 0.1, then here this is a minus 0.00001, and then a, or a plus zero point 0.1, and this is a plus 0.00001, and then a, and this is approaching from right hand side, and this is approaching from the left hand side. Okay. And and now some important study tips. uh, Now I'm going to say some important points that that will that will be often used in this chapter, limits. And a number that is, uh, for example, if L is a number and this is said to be the limiting value, and this limit L will be said to the limiting value of f of x as x tends to a, only if this L is real and finite. For example, it is root 2, root 5, 68, or any real number, uh, and should be finite. uh, Only then we will say that limit exists. Uh, else else we will say that limit does does not exist. uh, either should be fine, should be L should be real and finite. Only then we will say that limit exists. Otherwise, in all cases, we will say that limit does not exist. Uh, and for short form, we will use D and E. And what does this says finite? It means that, for example, if the function is y equal to y equal to fx, and fx is 1 by x, as x tends to 0, this function tends to infinity, so that is not finite. If we draw the graph of y equals to 1 upon x, it would look something like this. And in the chapter of coordinate geometry, you will see that this is also called as rectangular uh, hyperbola. This is also called as rectangular hyperbola, although we do not require this name in this chapter, but this will be required in the chapter of coordinate geometry. So leaving aside this, we are interested that as x tends to 0, this graph approaches to infinity from right hand side, and minus infinity from the left hand side. So so the limit is not finite, so we will say that limit does not exist. That is, limit does not exist at x equal to 0. Okay. And please note that a need not to be in the domain of f. Even if a happens to be in the domain of f, that is function, the value of a function at a plays no role in determining whether limit of x tends to a of fx equal to L. It is only the behavior of fx for x near a that concerns us. For example, taking this example only, uh, if we if this point would not have been there, then then we would say that there exists no value of function at x equal to a. So we will say that x equal to a is not in the domain of y of the function y equal to fx. Mm, so so the value of f of a does not exist, as a is not in domain. Okay. But in the neighborhood of a, there exist values y1. So we will say that the limit of a function f of x, as x tends to a, is equal to y1. That is that is limit of this function at x equal to a. And please note that the limit of the function at x equal to a does not mean that the actual value of that function at x equal to a. It just represents the neighborhood, the neighborhood values of a function at x equal to a. Please note this point. Uh, this this would be required in this chapter further also. And also, if and also this would be also an important point, that limit exists only if a left hand limit is equal to right hand limit. And what is left hand limit and what is right hand limit, we will study this further. And telling in brief, for example, at x equal to a, let the function would be like this, and there is a discontinuity here, and the function is like this. So limiting value of x, that is the value of a function y equal to fx in the neighborhood of x equal to a. It should be like a left hand limit would be the value of a function at just before x equal to a, that is something that, let's say y1, and here let's say y2. So uh, so here we would say that limit does not exist, because we would not be able to specify a specific value that for a function in the neighborhood of x equal to a. So we would say that limit does not exist in this case also. Okay. So moving on further. And also the statement that limit f of x as x tends to a equal to l is a statement about the values of f of x when x has any distinct value from but differing by little from 0. It is not a statement about the value of f of x when x is equal to a. When we make the statement, we assert that when x is nearly equal to 0, or x minus, or general rather generalizing it as x minus a tends to 0, f of x is nearly equal to l. We assert nothing about what happens when actually actually equals to 0. For example, if we take the example, uh, find limit x tends to 2 of the function x cube minus 3x plus 2 upon x minus 2. Pause the video to give a try, and then continue to see the solution. Now we know that x equal to 2 is not in our domain. Mm. Uh, as if we put the value of x equal to 2, it would be 0. The denominator would be 0. So x equal to 2 is not in the domain. So so we are interested in only in the values as x tends to 2, 2 plus or 2 minus. Okay. And also like this is 2. this is 2 plus del and this is 2 minus del. As del approaches to 0, this is also approaches to 2 and this also approaches to 2, but but this would be always greater than 2 and this would be always less than 2. So for the simplification we represent it as 2 plus and this as 2 minus. Okay, so now first we would see that as x tends to do 2, the denominator would approach to 0. And we see that numerator, we see the value in the numerator as x tends to 2, this this would approach to it should be here x square. So as x tends to 2, the denominator and numerator both approach to 0. So we could not make out what would be the value of this by directly putting the values in it. Okay. And we would study that this 0 by 0 is also called as indeterminate form, but uh, but we would also see that this function can also be simplified as x minus 2 times x minus 1 whole by x minus 2. So cancelling this common factor, the function would be y equal to x plus 1. So its limiting value as x tends to 2 is 3. So that's the answer. And if we would draw its graph, it would be simply the graph of y equal to x plus 1, except at x equal to 2 there would be an open circle which would be represent that x equal to 2, the function is not defined, but the limit is defined. Um, and we know that the limit just represents the value in the neighborhood of x equal to 2. So we don't have anything. What is the value of the function at x equal to 2? Okay, so moving forward, and now let's do a few good examples. um, for example, some oscillating functions. For example, if we would take the function as y equal to e power minus x sin x, and we would study its graph. Okay, so so we see that mm, that and also we know that sin x belongs from -1 to 1. Okay, this is the range of sin x. So we could say that y for all x greater than 0 is less than or equal to e power minus x and greater than equal to e power minus x whole negative. And if we would draw its graph, it would just look like this, like uh, like this is the graph of e power minus x. Its y-intercept is 1, and the graph of e power minus x, its y-intercept is -1, and the value of function of y would always remain in this, and its exact graph would look something like this. And then it would keep on oscillating, and at infinity it would approach to 0. And in further class we would see that this is all this is also called a sandwich theorem, that if the function y is sandwiched between the two functions, that is if the function y is always less than one function, and always greater than the second function. Or always, and or this equality holds even if for a certain interval, and at some value of x, if these two functions, that is these two functions, approaches to a certain value, then we would say that the limit of this function would also be equal to that function. That is the limit of that function at x tends to a. Okay, so continuing further,